Welcome to our discussion on all of these formulas, or as I like to say, fun with formulas, because that's all we're doing is formulas on top of formulas on top of formulas. Here are the objectives, right? We're going to look at the double angle and the half angle formulas. Those two are actually pretty good. They're helpful and useful. We're going to look at evaluating some expressions that involve inverse trig functions, and that really gets a little limited unless you're going to be moving on to calculus. You're really not going to need to deal with that at all. And then finally, I'm going to kind of just run through the product and sum formulas just in case your book covers that topic, because it's one of those fringe topics and very, very specialized formulas that most pre-calc classes don't even cover. And in fact, you don't even come across it in most calculus classes. So most of you can pretty much skip the end of the video. Okay, now everything we're going to be doing in here builds off of previous ideas and previous knowledge. Everything is still really being built off of the Pythagorean theorem identities, the sine squared plus cosine squared equals 1. And then we get the double angle formulas and half angle formulas. And then from those, we build off these product and sum formulas. It's all building on top of building. This is really what matters. The fundamental trig identities in the upper left corner, there's a reason why we call them fundamental trig identities, because they are fundamental to what we're doing, right? Everything is built off of that. First of all, we need to know how all these trig functions are defined in terms of sine and cosine, right? Because remember, everything is built off of sine and cosine. Then we have those Pythagorean identities. And as I've mentioned before, the second two, this one and this one, is really just a version of the first one. All you're doing is taking the first one and either dividing by sine squared or dividing by cosine squared to derive the other two. Then we have these even and odd identities, which really for the most part you could say who cares. It really comes down to whether or not the trig function is even or odd, and we've talked about what it means to be an even and odd function before. So these are kind of a no duh, really don't need to deal with it. And then even these cofunction identities aren't used a lot. They come up every now and then in calculus. You're going to see them in a pre-calc class just as a brain exercise, but they're really not that hugely important. Now, over to the addition and subtraction formulas. These we've seen in other videos, and they are very important. I would say these are second, right? First is the Pythagorean stuff. Then you've got the addition and subtraction formulas. Then third, the double angle and half angle formulas. And then the bottom stuff is really only useful in calculus. You do a lot of power reducing, lowering of powers in calculus when you're trying to take integrals. So these come in handy in that aspect. And then same thing over here. These come in handy for kind of U substitution techniques in calculus. So, use them here in a pre-calc class, put them on your set of formulas, and they're pretty easy to recognize when you have to use them, when you start seeing angles that are twice as big as they need to be, and you need to make them half, and vice versa. Otherwise, they're not going to be that helpful. Okay, so let's look at the double angle formulas really quickly. There they are, right? It's the idea that if we're trying to evaluate, let's say we know some of these special angles, right? We know what they are. For instance, we know what sine of 30 equals. Well, what if we have something that isn't 30? Well, we've seen before that if we had to do like sine of 75, we would use some of those previous formulas that we saw and go, oh, well, we'll break up 75 as to 75 as 30 plus 45, and then we can evaluate those. Well, this is just another set of formulas to help us solve those types of things. Now, sine only has one version. Cosine has multiple versions, but what's happened again is these two are just manipulations of this using the good old Pythagorean identity and doing some substitution. So it really depends on, do you want to take this function and turn it into something in terms of a cosine and a sine squared, or do you want it all in terms of sine and all in terms of cosine? And then the rest are the same kind of ideas. Now, as far as we're concerned in pre-calculus, these double angle formulas aren't really that helpful, because the idea is if I have sine of some angle here, then I want to turn it into sines and cosines where the angle is exactly half. Now, the previous formulas we had were really useful for when we wanted to solve for angles that weren't our special angles, right? We have the 30, the 45, the 60, and then of course 90. But those are our special angles. And so we can't get a precise answer for sine of 75. We'd have to stick that in our calculator and get a decimal. But then we learned, hey, we can take 75, we can break it up into 45 and 30, and then we can get precise answers. They'll be in terms of square roots, but that's fine. It'll give us an exact answer rather than a decimal out of the calculator. Well, these formulas in that same mindset would mean, okay, I know I can do a 30, right, or a 45 or a 60 for x, right? I can evaluate those. So this would help me if I ever want to do sine of twice of those. Well, sine of 2 times 30 is sine of 60. We know that, right? If we doubled 45, that's 90. We also know that. If we doubled 60, we get 120. And if you look on the right, if you do the reference angle for 120, it brings you right back to 60. So totally, absolutely, 100% useless for our purposes. All right, so why do we bother? Well, again, they're helpful. They're very helpful in calculus, because in calculus, it's all going to come down to taking derivatives and taking integrals. And when you take derivatives and integrals, you have to make sure that all of your trig functions, well, you don't have to, but it makes life a lot easier if all of your trig functions have the same angle. And so if you're trying to take a derivative of a cosine of 60 plus a cosine of 30, that's going to mess things up. Obviously, you wouldn't do 60 and 30 because those would be numbers. So let's say you were taking a cosine of x and then a sine of 2x. That's going to make life a little trickier. If you took sine of 2x and turned it into 2 sine x cosine x, that might make your life a little bit easier. So they're really going to help more for other classes, okay? But for your purposes in a pre-calc class, you just need to recognize that when you're given an angle that's twice as much as something else that you're working with maybe, or something else that you're trying to work with, you use these formulas to change it to that other size. All right, let's look at an example that we can do. Here, the instructions, right, when they tell you, hey, write cosine of 3x in terms of cosine of x, it makes it pretty obvious that I need to somehow change that 3x into an x, and that's when you start thinking, oh yeah, double angle formulas and other things, right? So 3x becomes 2x plus x. We use that sum formula, right? The cosine of alpha plus beta, which becomes cos minus sine. And then each of the cosine of 2x's, we use the double angle formulas and swap them out for something in terms of just x. And then for sine of 2x, we do the same thing. And now it's just a matter of kind of cleaning it up, doing the algebra right. Multiply this through so you get 3 of them, so it's cubed, and then times the -1. Bring that sign in here, which squares it, and there is our final answer in terms of x. Now, that's a lot uglier than cosine of 3x. And in an application world, you'd probably never do this, but that was what that book wanted you to do. So these are the techniques you're going to use. It really just becomes, remember, a lot of times we're not learning these things to learn about trig. We're learning these things to learn critical thinking skills. I'm presented with a problem, and I'm asked to perform a certain task, and I have a limited number of tools that I can use to perform that task, and it's all about figuring out which tool fits which task. Okay, so think about it in that mindset. That's really what we're doing. And then we can continue to play around with this thing, and we can factor things out and use Pythagorean identities, because remember, the question was in terms of cosine of x, and we had a sine squared here, so we have to sub out with a 1 minus cosine squared. So we can get it all in terms of cosine, we can combine like terms, and then we can finally get it down to this point here. And then, in a real world sense, it'd probably be better to then factor the cosine out, because we always like things that are factored. But, this is all we have to do for this one. Okay, so from that previous example, we can see that cosine of 3x ends up coming out to be a polynomial of degree 3 when it's in terms of just cosine. And the identity cosine of 2x, right, from our formulas, we saw one of the versions of it, the one that was in terms of all cosine, was 2 cosine squared minus x, and that's a polynomial in degree 2. And so just a neat aside, that lets us know that anytime we have a natural number remember is the counting number, so just integers that are positive, so 1, 2, 3, 4, 5, 6, 7. Anytime we have cosine of 1, 2, 3, 4, 5, 6, 7 x, and we reduce it down in terms of nothing but cosines of x. So if we started with cosine of 6x, let's say, when we did all the work and did all the substitution and got it in terms of cosine of x, it would have a bunch of different powers of cosine of x, and the highest power would be 6, right? So we always have a polynomial of cosines, and the degree of that polynomial, i.e. the highest power of cosine, is always the same thing as our n. And you're going, okay, great, thanks, big deal, move on. All right. Half angle formulas. Again, half angle formulas and are just other versions of the double angle formula. And from the half angle formula, we get the power reducing, or formulas for lowering powers. Here's an example of putting this one to use. All they say is express this junk in terms of the first power of cosine. I express it in nothing but cosines. Now they can be cosines of 4x or cosines of 2x. They just can't be cosine squared or cubed or anything like that. So all you have to do is straight substitution with the power reducing formulas, right? A sine squared becomes this stuff, cosine squared becomes this stuff, and luckily they both are in terms of cosine. You'll notice they're all in terms of cosine. Do the math, do the algebra, blah, 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 reduce it down, and here it is. So again, all you're doing when you see a question like this is if they're telling you to lower powers, you go, oh, doy, I'm going to use the power lowering formulas. Now, another way that we could have got to here was to use the double angle formula for sine in the form of sine x cosine x equals 1/2 sine of 2x. The double angle formula is really just a version of those sum and difference formulas. That's really where they come from, the sine of alpha plus beta. And all it is this is sine of alpha plus beta, where alpha and beta are both x, right? So if we go back up to here, sine of alpha plus beta, pretend that this is sine of s plus s, right? So s and t are the same thing. So wouldn't that be sine of 2s, right? So that's like our 2x. And so if you had s's and t's everywhere, so I'm sorry, if you had s's everywhere, because remember this is s plus s, you'd have sine s cosine s plus cosine s sine s. Well, isn't that just 2 sine s cosine s? Yes, it is. And that's where this double angle formula comes from. And the cosine one comes from the same thing. If you go up here and put in an s for both, you get cosine cosine minus sine sine. So cosine squared minus sine squared. Ta-da! Right? So like I said, everything builds on previous formulas. All they are is, if you want to memorize all of them, it's just, saving you the steps of having to derive them each time. All right, so back to this example, we plug those things in, we do the work, right? If we did it the other way and did the half angle formula, then everything gets squared and you end up getting the same answer. Okay, so here are those half angle formulas, because in order to get it back to regular power, you have to take a square root, and when you take a square root, you get plus or minus, right? And then you have to decide, is it plus or is it minus, and that all comes back from where the original function landed, right? So the plus or minus sign depends on the quadrant in which u over 2 lies. So what they mean is whatever this angle is, so if u was, let's say, 120 degrees, well, 120 over 2 is 60 degrees, and 60 is in quadrant 1. So if we were in quadrant 1, both sine and cosine would be positive, and we would use the positive version of the function. It's just that simple, right? If u was 200 degrees, then 200 divided by 2 is 100. 100 degrees is in quadrant 2, and sine would still be positive, but now cosine would be negative. Okay, so that's all you're doing. So now they give you this. Find the exact value of sine of 22.5, and you go, well, I don't know 22.5, but 22.5 is exactly half of 45, and I know 45. So let's use the half angle formula. And let's rewrite 22.5 as 45 over 2. Because then, using my formulas, I get 1 minus cosine of 45 all over 2, take the square root, and I'm going, okay, it's either plus or minus, but 22.5 is in the first quadrant, so sine is positive, so I take the positive version of it. And these get a little tricky as far as writing the answers are concerned, because cosine of 45 is square root of 2 over 2. So now we get 1 minus square root of 2 over 2 all over 2, and that whole thing is still in the radical. And I know that it's starting to make your head hurt thinking about how the heck can I have a square root inside of a square root. It's no different than taking the square of something and then squaring it again, right? Are you telling me that if we had something as simple as, let's say, 3 plus x squared, and then we squared it again, that would make your head explode? No, right? You would just FOIL that out, and you'd get a bunch of stuff. That's really no different than what's happening here. Square root of 2 just represents a number. It's 1 point blah, 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 blah. And then we're taking a square root of it when we're all done. It's just an operation on top of an operation, right? It's like adding and then adding again. Okay, so now we can clean it up a little bit. Remember the previous step was we had the square root 1 minus the square root of 2 over 2, and then that whole thing was over 2. All we did was do a common denominator up there. So we made it 2 over 2 minus the square root of 2 over 2, which is 2 minus square root of 2 all over 2, right? That's the top. And then it's still being divided by 2. And so what happens is when you have a fraction divided by 2, it's really a fraction times the fraction, right? So you get 2 minus root 2 over 2 times 1 over 2. Those come together, and that's why the bottom is now a 4. And then this whole thing is still under a square root. Well, of course, we remember our rules of square roots, that that's the same thing as the square root of the top over the square root of the bottom. And then this, of course, the bottom just becomes 2. So the whole thing is being divided by 2, which is the same thing as slapping a 1/2 out in front. And that's as simplified as it's going to get, right? You could leave it like this, or you could write it as the square root of 2 minus the square root of 2 all under a square root, and then the whole thing all over 2. Either way is the same thing. And you can put that in your calculator, right? It's not that difficult. But that is the precise answer. Once you put it in your calculator, you're going to get a decimal expression, and it's no longer going to be precise. Okay, inverse trig functions. It's funny, we call these things expressions involving inverse trig functions, but we can really do all of these without taking any inverses, because it all comes back to SOHCAHTOA and drawing a right triangle and solving things using the Pythagorean identity. So when they want you to, they give you some information and they say evaluate some things, you can always just draw a picture. So this particular example, they say evaluate sine of 2 theta, where we know what cosine of theta equals, and they tell us what the quadrant is. So we know we're in quadrant 2, so we draw a little picture. Cosine, is adjacent over hypotenuse, so that's where we get the 2 and the 5. Of course, the 2 is negative, right, because the hypotenuse is always positive. From our picture, we can now solve for this third side. By doing Pythagorean theorem, we know 2 squared is 4 plus, right, whatever y is squared has to equal 5 squared, which is 25. So y squared is going to equal 21, and of course y is going to be the square root of 21. Now technically it's plus or minus the square root of 21, but because we're in quadrant 2, we know it's positive, so it's just positive square root of 21. Okay, so here's that all worked out. And now that we have that, now that we have all those pieces, we can solve for sine of 2 theta using the double angle formula, because sine of 2 theta is just 2 sine theta cosine theta. And then we just plug everything in. So from our picture, we need 2 sine theta cosine theta. Well, we already know what cosine theta is. It's negative 2/5, right? Sine theta is just opposite over hypotenuse, so it's just square root of 21 over 5. We plug all those things in, we do the math, we simplify, and that's our final answer. That's it. You know, if they want a decimal rounded, we can round it. If they want a precise answer, that's the precise answer. Okay, now we're going to get into those formulas that most of you can ignore, the product sum formulas. And it's really, like I said, they're just being derived from the formulas we already knew, the sine of alpha plus beta, the sine of alpha minus beta, and so on and so forth. If we wanted to solve for certain things, we can just do some algebraic manipulations and go from there. So for instance, if we take the two sine formulas and we just add everything together, right? We're just pretending like we're doing a double-sided addition. All we're doing is adding everything up, right? So you add these two pieces together, and that's just that plus that. And when you add these two together, can you see that these pieces cancel because they're the same thing but with a plus and minus? And that's why you get 2 of the sine u cosine v. Now, if we wanted to solve for sine u cosine v, all we have to do is divide both sides by 2, i.e. multiply by a half, and there we have it, the product to sum formula. So if you're given the product of sine of u times cosine of v, and you want to turn it into a sum of things, then you can turn it into 1/2 sine of u plus v plus sine of u minus v. Wow, that makes my life so much easier, right? It's pretty stupid. We're not going to use it that much. And hopefully whatever class you're in, you're not going to use that much either. But again, it's just a derivation of the formulas you already knew. So put them on your list and know that if you're given a question that asks you to do exactly what these things do, then these are the tools you use for that job. Okay? These formulas obviously can go backwards and forwards. So you can start with a product and make it a sum, but you can also start with a sum and make it a product. So just make sure that you're always realizing that you can go back and forth, because sometimes you need to go in the other direction. And if we take the remaining 3 of these formulas, they obtain we get them all the same way. And so we can turn them in both directions. Product to sum, sum to product, they're really just doing the same thing. But it's all about recognizing what's happening. So you would recognize, if I have a sine of something plus sine of something, I can turn it into this stuff. If I have a sine of something times a cosine of something, I can turn it into this stuff, right? So it's all about what do I have and what do I need to get. But I can also go backwards. If I see this kind of weird stuff where I have sine of alpha plus beta over 2 times cosine of alpha minus beta over 2, I'm like, hey, that pattern reminds me of something. Oh yeah, I've got this formula here, right? So that's how you're going to tackle these types of questions. Verifying identities, same idea, where we know that, well, I've got a tangent of x here. I've got some 3x's, right, on the left-hand side. So I better reduce those somehow. And I'm thinking, well, I know that there are certain formulas that will reduce them. This is one way to go. I probably would have seen this as a sine of 2x plus x, right? And I would have gone right back to sine of 2x plus x, which turns into all this stuff. And then everywhere that I had the 2x piece, which would have been here and here, I would come down here and use my double angle formulas and plug in this stuff, get everything in terms of x's, and then just go to town with algebra, right? Just combine like terms and substitute stuff in and go that way, rather than going this way, which seems like magic that they would come up with this. So it's another reason why I say those formulas aren't that helpful, because you can almost always do it the other way with the other formulas. So I'm going to end on showing you this slide again. I would suggest that if you don't already have these written down somewhere, that you pause the video, use whatever screen capture technique you like, copy, paste it into a Word document, print it out, do whatever you got to do. But these are really the main formulas that you need to know.